Okay, now let's understand the difference between the heat capacity and specific heat capacity. Heat capacity, it's the amount of heat which is required to raise the temperature of entire body by 1 degree Celsius of entire body. And specific heat capacity is the amount of heat energy which is required to raise the temperature of unit mass of the body by 1 degree Celsius. Okay, of unit mass, not the entire body. That means of 1 gram mass or 1 kg mass. Okay, depending upon which unit you're using. Second difference is that heat capacity depends upon both substance and the mass of the body. More is the mass of the body, more is the heat capacity. Obviously, when you're talking about the heat capacity, we are talking about the entire body. So entire body can be of greater mass and of less mass also. So greater is the mass of the body, greater is the heat capacity. But in case of specific heat capacity, we're talking about the unit mass. So it doesn't depend upon the mass of the body, but it is the characteristics property of the body. Okay, whenever you're talking about the specific capacity, we're talking about 1 kg of iron, 1 kg of copper. It's a unit mass of copper. So no dependence on mass. It's a property, it's a characteristics property. Okay, specific capacity is one value for one substance. For water, just now you understood, it is 4180. Just now you got it. For copper, it is 385. For iron, it is 554, like that. So it is different for different substance, and all these are specific capacity values. Third, we can formalize the third difference. C prime, the heat capacity is Q by delta T. Okay, and in terms of specific capacity is mass into specific capacity, but specific capacity is Q divided by M delta T. So it is heat capacity per unit mass. Okay, Q delta T is the heat capacity, so per unit mass is the specific heat capacity. That's the only difference between them. Number 4 is the unit. So it is joule per Kelvin. Joule per Kelvin. Here it is joule per kg per Kelvin. That's the unit. So these are the 4 difference between the specific capacity and heat capacity. Okay, next let's understand specific heat capacity of some common substance. The specific capacity of any substance is a characteristics property. Characteristics property means that it is different for different substance. Okay, it's a characteristics property. Okay, for example, good conductor like copper, iron, these are good conductor of heat. They have low specific capacity, and for bad conductor, they have high specific capacity. For example, the specific capacity, of water, you can see it is 4180 joule per kg per Kelvin. So it is maximum for water. And for it is copper, it is 385 joule per kg per Kelvin. So low value of specific capacity means it is good conductor of heat, and the high value of specific heat capacity means it is a bad conductor of heat. In terms of the same thing for water, in the specific capacity value for water, it is 4.2 joule per gram per Kelvin. So in different unit, it is 4.2 joule per gram per Kelvin. Okay, and the copper, it is 0.4 joule per gram per Kelvin. Here in the table, it is given in terms of SI unit, which is joule per kg per Kelvin. Here they have given in terms of joule per gram per Kelvin. So that's the difference, but it's the same thing. For copper, it is 0.4, and for water, it is 4.2. That means the specific capacity for copper is less compared to the water. It's much less. That means copper is a good conductor of heat because it only needs very small amount of heat to raise the temperature. It only needs 0.4 joule amount of heat. Okay, if you have a copper of 1 gram, then to raise the temperature of 1 gram of copper by 1 Kelvin, you just need 0.4 joule amount of heat. But if you have water of 1 gram, and if you want to increase the temperature of water of 1 gram by 1 Kelvin, then you need 4.2 joule amount of heat. That is much more compared to this. Therefore, we can say that water is a bad conductor of heat, but copper is a good conductor of heat. So depending upon different substance, okay, the value of the specific heat capacity, the amount of heat which is needed to raise the temperature would be different. Okay, if it is the specific capacity value is less, then the amount of heat which is needed will be less again to raise the temperature. Okay, so substance with low specific capacity shows a rapid and high rise in temperature. Very simple. Thus it is a better conductor of heat than the substance with high specific capacity. Why? Water has very high specific capacity, so water is a bad conductor of heat because it shows a slow and small rise in temperature. Okay, that means I have to give 4200 joule amount of energy to 1 kg of water if I want to increase the temperature by 1 Kelvin, okay, which is very high, unusually high. Here also there's some note which is important. The specific capacity of the same substance, for example water, is different for different phases. Okay, the specific capacity of water is 4200 joule per kg per Kelvin, that we know, but for ice it is 2100 joule per kg per Kelvin. Water and ice are the same thing but two different phases, so it also changes with phase also. For water it is 4200 joule per kg Kelvin, and for ice it is 2100 joule per kg per Kelvin, and steam it is 460 joule per kg per Kelvin. Okay, steam it is less, so keep that on. The specific capacity is maximum and it is equal to 1400 630 joule per kg per Kelvin for hydrogen. So for hydrogen the specific capacity is maximum, which is 1400 630 joule per kg per Kelvin. Okay, principle of method of mixture or principle of calorimetry. What does it mean? It means suppose we have a hot body and we keep this hot body in contact with the cold body, then we know that heat will flow from hot body to cold body. Suppose these two bodies are kept in such a way there is no heat loss to the surrounding, then according to principle of calorimetry, the heat energy lost by the hot body should be equal to the heat energy gained by the cold body. So this is what is the principle of calorimetry. So two bodies are kept in contact, then whatever the heat energy lost by the hot body should be equal to the heat energy gained by the cold body if there is no energy loss in the surrounding. Okay, let's try to understand that mathematically also. Suppose we have a substance A of mass m1, okay, and the specific capacity c1 at higher temperature T1. We have one substance with mass m1, specific capacity c1 and temperature T1, okay, which is high temperature, and it is mixed with another substance B of mass m2, specific capacity c2 at lower temperature T2. Okay, so T2 is less than T1. So let's say, and if they are mixed together, then obviously the higher temperature body will start losing the temperature and the lower temperature body will start acquiring the temperature. And let's say the final temperature attained by both in the equilibrium, okay, is T. So final temperature is T. Okay, then obviously the fall in temperature of the substance A is what? T1 minus T, because T1 is the higher temperature. So this, because obviously in substance A there will be fall in temperature, in substance B there will be rise in temperature. So fall in temperature is what? T1 minus T. T is the common temperature and T1 is the initial temperature of substance A. Therefore T1 minus T is the fall in temperature. What is the rise in temperature? Rise in temperature in substance B would be what? T is the common temperature and T2 was the initial temperature, which was low temperature. So T minus T2 would be the rise in temperature for the substance B. Okay, it's just like suppose substance A has a temperature initially 15 and substance B has initially temperature T2 suppose 5, and the common temperature when they are 10 after in equilibrium is suppose 10, then the fall in temperature would be what? 15 minus 10, and rise in temperature would be what? 10 minus 5. So that we have to find. So T is the common temperature after equilibrium, okay, when the two substances are in contact. So heat lost by the body would be what? Q equals to mc. T is the general formula, mc change in temperature. So heat lost by the body A is m1c1 fall in temperature. Okay, so m1c1 T1 minus T, the formula. Heat energy gained by the body would be what? m2c2 rise in temperature, which is T minus T2. So this is the heat energy lost and this is the heat energy gain. So according to the principle of calorimetry, if there is no heat lost to the surrounding, then this heat energy lost should be equal to heat energy gain. So I equate these two equations. So above equation can be used to calculate the unknown quantities. Suppose m2 ec2 is given and T minus T2 is given, then you can always find C1. So whatever is like, you can use this kind of equations to solve questions, solve numericals. Okay, if one of the quantities are known, then other quantities can also be found out. Can be found out. Okay, fine. Let's understand natural phenomena and consequence of high specific capacity of water. So you know water has very high specific capacity, which is 4200 joule per kg per Kelvin. So let's try to understand what are the consequences of this high specific capacity of water. The first consequence is that the climate near the seashore is moderate. Why the climate near the seashore is moderate? Neither hot nor cold. Why? The main reason is that the specific capacity of water, you know, is very high, which is 4200 joule per kg per Kelvin, or 1000 calorie per kg per degree Celsius in another term. Okay, so which is almost 5 times greater than that of sand. That, okay, so obviously that means the sand has 5 times less specific capacity compared to the water. What does it mean? It means if you want to raise the same temperature of same mass of sand and water, that means in that situation for water we need 5 times more amount of heat compared to the sand. Okay, so because of that reason only, during the daytime, since the specific capacity of sand is very small, almost 5 times less compared to the water, so sand gets heated up very fast compared to the water. Yes or no? Okay. And similarly, during the cooling time also, for the same fall in temperature, whatever the heat is lost by the sand, the amount of heat lost by the water will be 5 times that of sand, because it needs 5 times more heat to increase the temperature. Obviously, while losing the heat also, it loses 5 times more heat for the same fall in temperature. So keep that in mind also. Okay, so during daytime what happens? The sand has very less specific capacity compared to the water, 5 times less specific capacity compared to water, therefore it gets heated up very fast. And so what happens during the daytime, the breeze from the sea, there's a temperature difference. Obviously in the sand region the temperature is high, in the sea region, the water region, temperature is low, because water gets heated up very slowly. So wind from the sea moves towards the land, cold wind, okay, which keeps the temperature moderate. Again at night what happens? At night sand releases heat very fast, so the sand becomes cold very fast, but the water region, it releases heat very slowly because it has high specific capacity, therefore there is a rise in temperature takes place very slowly also, and releasing heat also takes place very slowly. Because of that, again there is a temperature difference, and the wind from the land starts flowing towards the sand. The wind from the sand starts flowing towards the sea, so there's a land breeze also at night. So there's a land breeze and sea breeze, both flows towards each other, okay, in different situations. The sea breeze flows from sea to the land, and land breeze flows from land to the sea. Okay, so this way these breezes make the climate near the seashore moderate.